an important thing to note about forces is that they are vectors, okay? And they add up when acting on an object. Just consider the case of you're trying to move a heavy object along the floor. Okay, let's say this is the refrigerator, okay, and you're trying to move it into place. You just got a new refrigerator and you're trying to move it into place. Okay, it's pretty heavy, and so you ask your friend to tie a rope around it and pull on that rope. Okay, you're pulling on that rope, and you are pushing on it from behind. Got really long arms there. Okay, so you're pushing and pulling on that rope to try and get it into place. Well, what are all the forces acting on that? Okay, why do you need your friend to pull while you push? It's because the forces add up to a net force. So what we care about is the net force acting on an object. Okay, so looking at this fridge, I could see, here's a push right there. Here's a pull in the form of a tension right there. Okay, this would be a contact force. You can call it F push or whatever. You could even call it a normal force if you wanted to. There's a traditional normal force from the floor holding it up. There's a normal force there. Okay, we'll put a T here, or write out tension here. Here's a push there. Okay, and there's a force of gravity acting on it. Remembering that gravity is our only long-range force. Okay, now there's still one more force that we haven't seen. Why is it hard to push the fridge across the floor? Is it just because it's heavy? Okay, if it's heavy, that does make it difficult to accelerate it, but there's another thing that's causing the bulk of the problem. If the fridge was on really well-oiled rollerblade wheels, would it be hard to push? The answer is no, it wouldn't be that hard to push. Okay, but the reason why it's hard is because it's rubbing along the floor. There's a lot of friction involved. And so also at that interface we have friction working against it. So how can I make sure I record all the correct ones and not record incorrect forces? Okay, the way we can do that is to talk about a force identification diagram. So let me do a second example to try and understand that. Let's go ahead and put a book on an incline. Okay, the way we can try and identify all forces is we draw a circle around the object. Okay, that does one thing. It identifies our object. Okay, it identifies our object. We need to make sure we know which object we're talking about. Like here, I see 3 objects. You might even say 4. There's a rope. Okay, what am I talking about? Well, net force on what? So we need to identify, well, what object are we trying to find the net forces on? By drawing a circle around the object, it helps us to clarify, okay, I'm talking about that one. No matter what is acting on it, I'm talking about that object. Okay, by identifying that object, now I can think, okay, what's acting on it? First, I could say, is it in space, or is it on Earth, or is it on the moon, or something like that? Is there a significant gravitational force? So most of the problems we'll deal with are problems that we would interact with daily. Things, cars and balls and stuff that interact with gravity all the time. And so we can draw a little arrow to the center of the object, just pointing to the object itself, and write down gravity. Okay. And then once we've established that long-range force, again, in this course, that will be the only long-range force we have to deal with. But then we can talk about all the other forces. Say, okay, well, what's acting on it? Where are there contacts? That's what the circle does, is help me to identify any contacting points. Okay, now I see only one contact between this object and the environment around it. I see the contact with this tabletop. Okay. Now, the tabletop is doing 2 things. One, it is keeping the book from falling through the table. That's the normal force. It's pushing outward. It's pushing outward on the book. Okay, pushing it away from itself, from the interface. Okay, but at this incline, there's also there also must be friction. Otherwise, this book would be sliding down. If there's no friction, if I put this book on a slick Teflon surface or ice or something like that, it would slide down. Okay, but it's not, which means there's another force, and it's caused by the same interface, but it's in a different direction. It's pulling it up the incline, or pushing up the incline, while that component of gravity is trying to pull down. So there's also friction here. Okay. Now, technically there's air molecules around it and it's interacting with those, but if an object's not moving, or even not moving significantly, we're not talking about jets, airplanes, cars moving at high speed even, the air drag is fairly insignificant. Well, if it's not moving at all, there's no air drag, but even for normal moving objects, air drag's not as big of a deal, and we can neglect it often. Now, we will get to the point where we can include air drag and see its effect on a jet trying to speed up or something like that, where the air drag is calculable. We can calculate it. But we will focus a lot on situations where air drag is negligible. In the case of this book, there's no air drag because it's not moving. Okay, so that is now complete. Now you might argue and say, duh, I could have done that. I didn't need to spend 6 minutes in talking about this, the forces on this book. I want to remind that the process here is what's so important. We're trying to learn a process to be able to analyze complex situations. Sure, this is a fairly simple situation, but there are some subtle problems, even in very simple situations, that we make common mistakes by not accounting for certain forces or suggesting there are forces that don't really exist. And it's this process that allows us to do it. Now, this particular step, this force identification diagram, we won't do forever. This one is a method to get our minds thinking properly about accounting for forces. And so you should always be accounting for forces and making it a deliberate part of the process. But we might not always need to draw out a diagram. We will until we've sufficiently habitualized that process. Okay, so this is called a force identification diagram because we're just identifying. Identification diagram. Because we're just trying to identify forces, making sure we have all the correct forces and no forces that don't really exist.